Hello and welcome back to C++ Real-Time Audio Programming with Bela. I'm Andrew McPherson, one of the original creators of Bela, and today I'll be taking you through a first look at writing C++ code that generates audio in real time. In case you're just joining us, this class will teach you to create the components of modular synths using Bela, which is an open-source embedded hardware platform. These are some of the programming topics that we'll cover. In general, each programming topic will be associated with one or more music and audio topics. Today, specifically, we're going to be looking at what it takes to write code that runs in real time, and we'll be creating oscillators by way of examples. Specifically, today you'll learn what we mean by real time and what we need to consider for our code to run in real time. By the end of the lecture, you'll understand how to create sine wave oscillators in C++. Now, the companion materials for this lecture are on GitHub, and they include code examples that we'll work through together later on in the lecture. For those just joining us, we expect that you have a Bela starter kit or a Bela Mini starter kit to run the examples, though of course you can follow along without one. Later lectures are also going to use some basic electronics, although you will not need any of these components today. Now, to learn how to get started with Bela, go back to Lecture 0 in this series, but I just want to highlight one thing in particular, which is that to run the code in this lecture, you will need to update your Bela software to the latest version. You can do that from the Bela IDE or through the terminal, and again, for more instructions, go to the previous lecture. Okay, let's dive in. This is a class about working with digital signals. And when we talk about digital signals, all we're really talking about is a series of numbers ordered one after the other. So a signal x of n is defined for integer values of n from minus infinity through infinity, and undefined when n is not an integer. Now, in theory, a discrete time signal doesn't have to represent any particular quantity in the real world, but often in more informal usage, especially for audio, digital signals are oftentimes considered to be sampled versions of some hypothetical continuous analog signal. This would be written x of t with parentheses rather than square brackets, and it would be defined for all values of t, not just the integer ones. So in this example, we could write x of n is equal to x parentheses n times t, i.e., each value of x of n represents a particular sample of the continuous signal x of t. We could also talk about the sample rate of this signal, which is defined by 1 divided by capital T being the sampling period. Now, if all of this terminology is completely new to you, don't worry, we're not going to spend a lot of time with it here, but there are a number of great resources that you can find online, some of which are listed in the previous lecture's companion materials. This is a class about real-time audio programming, so let's talk about what we mean by real-time. Basically, we mean processing or generating signals as they come in, as opposed to doing it all in advance. So if we had a signal x of n whose samples were arriving one after another in time, then a real-time system is one that is processing the values of x of n piece by piece as those samples are arriving, rather than waiting for the whole signal to arrive and then processing it all at once. So we can contrast these real-time systems to non-real-time systems that we might find, for example, in audio editors, where they have the luxury of having the entire sound file laid out in front of them, and they can do operations on all the samples at once. Some particular kinds of processing might actually require that you have the entire sound file before you can do this. Now, I want to stress that real-time is not a theoretical concept of DSP theory. It is a practical implementation consideration about the system that we use to build a DSP system. That our theory doesn't actually care about what n actually means, whether it is a sample of a continuous time signal, what that sample rate is, or what kind of hardware is processing it. The only real exception to this is for a mathematical system to be possible to implement in real time, that system has to be causal, which means that the current output of the system depends only on the current and the previous inputs and the previous outputs, and not dependent on anything that would happen in the future. Being able to implement a system in real time depends on how we structure our computation. And there is one key criterion for making a real-time signal processing system, and that is that every computation must finish in a bounded amount of time. The idea is that the result is only useful if it arrives on time. If it arrives late, it might as well not have happened at all. Now, this doesn't necessarily mean that the result needs to arrive particularly quickly, only that there must be some period of time that we can always guarantee that every computation will be finished in. So here, we can see that our input signals are turned into an output signal by some calculation, and that calculation always finishes within this particular period of time. An analogy here would be if you're packing widgets into boxes on an assembly line. The idea is that you have a certain amount of time before the assembly line moves on. You have to be finished with your packing by that point, and if you're not finished, then you might as well have not packed that box at all. Now, there's one other consideration for being able to implement a system in real time, which is that on average, it can't take any longer than one sampling period to process one sample. If this wasn't true, then we would gradually fall further and further behind, and there would be no way to meet our bounded time criterion. So in this example, here we have the maximum average amount of time that the computation can take, even as we have a relatively longer amount of time before the result needs to be ready. Now let's look at a practical example. Maybe you recognize this equation, maybe you don't. This is an equation for an IIR filter, which stands for infinite impulse response. If you haven't seen this before, don't worry about it. There are lots of great online resources about these concepts, but you won't need it to work with the code examples today. Now suppose I told you that this was an 8th order filter. My question to you is this a real-time filter? Now, that might be kind of a puzzling question because you could say, well, actually we really don't have enough information to know whether this is real-time or not. This really depends on how the filter is implemented. Okay, so I'm going to tell you now that it takes 10 milliseconds on our hardware to compute a single value of y of n for this filter for every new x of n. Now is it a real-time filter? Well, that still depends. We don't know. What more do we need to know about this? We need to know, what is the sample rate of the system? Is it taking longer than 10 milliseconds for each successive sample to come in, or are the samples coming in more rapidly than 10 milliseconds? Because if the samples are coming in more frequently than 10 milliseconds, it can't possibly be real-time because we'll fall further and further behind. So finally, I'll tell you that the sample rate is 50 Hz. The sampling period is 20 milliseconds. Now is it real-time? Well, maybe. It could be real-time under these circumstances, but it is still up to us to come up with an implementation that guarantees that we'll finish every computation in a bounded amount of time. Now let's switch topics and talk about some of the resources that we would use to implement real-time systems. There are a variety of types of processor that could be used to implement audio code. One of them, and the most frequently encountered, is the general purpose processor. This is your Intel or your ARM chip that powers your laptop or your phone. These processors are jacks of all trades designed to do a variety of tasks reasonably well. There are small low-power versions of these processors which are called microcontrollers. This is what you'll find on boards like Arduino, for example. We could contrast this with digital signal processors. Now this is distinct from digital signal processing as an activity, and it actually refers to a specific architecture of processor that's very good at doing maths very, very fast, but is perhaps less flexible for other kinds of operations. You'll oftentimes find these in dedicated hardware boxes and sometimes as co-processors within system-on-chips. Another kind of processor that you'll encounter a lot is the GPU, or graphics processing unit. GPUs are extremely good at massively parallel data, things like video pixels, where you're calculating lots and lots of operations all in parallel on lots of different numbers, but with relatively little interdependence between those computations. You can use GPUs for audio, and it's actually an area of current research, but it's not something that we're going to talk about in this course. Finally, you will also see people processing audio using FPGAs, which stands for Field Programmable Gate Array. This is essentially programmable hardware where you encode gate-level logic to perform the particular operations that you want to do. When you're done, it's extremely fast, but not versatile at all. And so you can see that across this spectrum of options, we have a trade-off between generality and performance. In the case of Bela, it runs an ARM Cortex-A8 processor, which is a form of general-purpose processor. And you'll actually find in this day and age that general-purpose processors have often surpassed digital signal processors for calculating audio. Let's also talk about the kinds of operating system you might run on that processor. We have our familiar general-purpose operating systems, Mac, Windows, Linux, Android, iOS, etc., basically designed for typical applications on computers and mobile devices. The idea of the general-purpose operating system is that it shares time between a number of simultaneous processes, all of which get to run approximately at the same time to maximize the overall performance of the system. You can oftentimes give certain processes higher priority than others, but you can't generally make ironclad timing guarantees about when a particular process will run. We can contrast that with real-time operating systems, or RTOSs. These are designed for more mission-critical applications where we do want to be able to make ironclad precise guarantees about how long it will take to run certain code or how often certain code will be able to run. There are examples of real-time operating systems running on everything from high-performance processors to small microcontrollers. Bela itself runs a real-time operating system, which is Xenomai. Xenomai is a set of extensions to the Linux kernel that lets you run certain tasks at guaranteed high priority on the hardware. Finally, if our application is relatively simple, we might not need an operating system at all. If you're using a microcontroller, then you might just run your code directly on the hardware, sometimes called bare metal. This doesn't preclude you from having asynchronous events, which you can use hardware functions like interrupts to do, but it can simplify your code enormously and let you make timing guarantees. However, it's not as powerful or as flexible as having an operating system available. Finally, let's talk about a distinction between two different flavors of real-time. We can talk about hard versus soft real-time, and the difference here is basically whether guarantees can be made about the timing. In a hard real-time system, we can come up with some fixed amount of time that we can guarantee the results will always be available in, without exception. This is very useful for safety-critical systems in industries like aerospace and medicine, where a missed deadline could have catastrophic consequences. And we could contrast this with soft real-time, which essentially means that most of the time the calculations finish on time, but that we can't necessarily guarantee it. This is suitable where a missed deadline is an annoyance, but potentially not a catastrophic failure, cases like streaming audio or video games. Whether real-time audio demands hard or soft real-time performance depends on your perspective. If you're a consumer streaming audio on your computer, then maybe it doesn't matter if there's the occasional click or pop, but if you're a professional musician playing on stage, then clicks and pops can really undermine your performance. So this is the reason that on Bela we have created a hard real-time system using a real-time OS, Xenomai, but running on a general-purpose processor, which is an ARM processor. Okay, that's enough theory and background. Let's get on with our first project. On the companion materials on GitHub, you can download the projects for this lecture. You'll find one called sinegenerator.zip. Now, for more details on how to upload projects into Bela, you can see the previous lecture, but it's really quite simple. You just drag the zip file into the Bela IDE window, and you'll see a window pop up asking you what to name the new project. If you do that and you don't see that window pop up, you probably don't have the latest version of the Bela IDE, so go update that now following the instructions from the previous lecture. Then once you've uploaded the project, you can click Run to start it. Okay, so here I have my projects from today's companion materials, and I'm going to take the project called sinegenerator, and I'm going to drag this into the Bela IDE. I'll do that, and it'll ask me, do you want to create a new project? Yes, I do. Click Create Project, and what we'll see is that it'll unzip it, and it will make a new project called sinegenerator. And then all I have to do here is click the Run button to build and run that project. Now, you may find that if you have just updated your Bela IDE, that it'll take a few minutes to build all the rest of the files, but every subsequent build should be quite fast. Okay, now when you've heard the sine wave, you can stop the project, and let's just have a brief look at what's going on. So the key feature of the sinegenerator project is that it does not generate audio in real time. Sinegenerator is instead calculating a whole signal once at the beginning, storing it in a big buffer, then playing it back and saving it to a file. Although the audio playback is itself real time, we are interested in the calculation of the sine wave. Now, specifically, we have this function called calculate sine. The idea is that this runs once at the beginning and generates the entire 5 seconds of audio. Within calculate sine, you can see there is this for loop. Now, if you have not seen a for loop before, there are a number of really good tutorials on C, C++ that will take you through more details of this, but the essential idea is that this is a way of writing a block of code which runs a fixed number of times in a loop according to certain conditions that you specify. So what we're saying is that this code is going to run num samples times. And so we have this variable called n, which starts at 0, and it gets gradually bigger and bigger until it reaches the value num samples, and then the loop stops. So this is going to run potentially tens of thousands of times to generate 5 seconds of audio at 44,000 samples per second. The crucial line is this one. Float out is equal to g amplitude times sine of 2 times pi times n times g frequency divided by sample rate. What's going on here is that the current phase of the sine wave is a function of the sample number n, which starts at 0 and goes progressively upward across the 5 seconds of audio. And the formula for this is not something that we're going to go into in a tremendous amount of detail, because what I want to focus on is the real-time implications of it. The final thing to say about this block of code is that once the output is calculated, it's stored inside of an array, and we'll talk more about arrays and buffers in the next lecture. So what's happening here is that we're calculating a series of numbers over time, a digital signal, and these are going to be stored inside the variable called buffer. So buffer index 0, buffer index 1, 2, and 3, these are successive samples of the sine wave over time. Once we've calculated all of them, then we'll play them in real time. As I said, the problem here is that sine generator is not calculating its values in real time. Our goal is to implement a real-time generator, and so the question is, how do we do that? Well, we know that digital audio is composed of samples. We know that in this case, Bela is operating at 44,100 samples per second. What that means is that we need a new sample every 1 over 44,100 seconds, i.e. we need a new sample every 22.7 microseconds. That's our sampling period. Now, what we could do is every time we need a new sample, we could just run a short bit of code and calculate that sample as we need it. So it seems plausible, but there are drawbacks. And what might that be? Well, a drawback of this approach is that there is not just our audio code running on the computer. There are lots of different processes running at the same time. And we really are not sure that we can guarantee that we're actually going to be able to get to our audio processing within 22.7 microseconds every time we need things. So here's a little exercise just to illustrate the problem. Go over to the Bela IDE, and in the terminal at the very bottom line of the IDE, you can type PS and hit enter. And what you'll see is that it'll scroll through a bunch of text, which will list all of the processes that are running on the board. So there are actually dozens of different processes that are running on your Bela board all at the same time. Each one takes some load on the CPU, takes some amount of memory, and the job of the OS is to switch rapidly from one to the next. And it's even worse because within those processes, every individual process might contain multiple different threads of execution. And so we have a real problem. We can't guarantee that our audio code is always going to run within 22.7 microseconds because the system might be busy with something else at the time. The usual solution to this problem is that rather than processing samples one at a time, we process them in blocks. The idea is that we generate ahead enough samples that we can get through a few milliseconds of audio, and then the system can go away and do other things, and then we can come back and generate another block of samples. On a typical Mac, Windows, Linux system, you might find block sizes between 32 and 512 samples. Usually they're a power of 2 just because there are reasons that that's more efficient to implement. On Bela, because of the Xenomai real-time operating system, we can get a much faster response time with tighter guarantees on our timing. What that means is that we can use much smaller block sizes, potentially as low as 2 samples. We'll come back to this in a later lecture, but the default on Bela is 16 samples. The idea then is what we're always doing is essentially staying one step ahead of the hardware. The hardware is going to be playing whatever the block is that we just calculated, and meanwhile the processor is going to be busy calculating the next one. So if we're calculating block 2, the hardware is playing block 1. By the time the hardware finishes, we're on to calculating block 3, so we're always staying one step ahead. And then within each block, there will be a series of samples. It might be 8 or 16 or 32, depending on the block size. Now, the advantage of working with block-based processing rather than one sample at a time is that we need to call our code that calculates audio a lot less often. We can generate one block ahead, and that means that if our block takes a certain amount of time, but running our code only takes a fraction of that amount of time, then whatever is left is available for the operating system to do other things. And what's more, we can tolerate the operating system delaying our code by that amount of time before our code runs. So what this means is that the larger the block size you choose, the more tolerance you will have for timing variation. And you may have noticed this in audio code on your computer, that sometimes if you have a program that is getting glitches or pops in its audio, you can resolve it by setting the audio block size to be something bigger. Nothing comes for free, of course. There is a disadvantage. What is that? Well, it's latency. It's that the bigger the block size, the longer the delay between calculating a sample and actually hearing it. This will be the topic of a future lecture. Right, so for our second project in this lecture, I want you to put onto the board the project called Sine Generator RT. This is from the same folder in the GitHub companion materials, and you create the project in exactly the same way. What you'll find is that when you upload this project, it won't compile straight away because there is a line missing, and you're going to need to copy one line from Sine Generator, which calculated the value out, into Sine Generator RT, and you'll need to make one more substitution. There's a variable in there called sample rate, and it needs to be replaced with the expression you see here, which is context, little arrow, audio sample rate. And once you've done this, you should be able to compile the program. You should be able to, and you'll be generating code, and you'll be generating audio not in advance, but in real time. And what I want you to do now is pause the video here, run it, and see how it sounds. Here I am in my Sine Generator RT project. You'll see that we have this line of code which is not filled in. That's a bit of a problem because it won't compile, so what we need to do is copy it from Sine Generator. So I'm going to open Sine Generator here. I'm going to go down to calculate sine. I'm going to copy that magic line that we talked about. Go back to Sine Generator RT, paste it in here. And by the way, you can have multiple tabs open in the Bela IDE with different projects in them, and that can save you some time. So here we are. You'll see that it's still complaining undefined variable sample rate, so we have to do that substitution that we talked about in the slides, which is to replace this with context arrow audio sample rate. We'll learn more about this in a later lecture. And now you should be able to run this program and hear what it sounds like. And it sounds awful. We don't know what that is, but it is absolutely not a 440 Hz sine wave. It is this nasty, high-pitched buzz. What's going on? Well, back to the theory. Why does this sound distorted? Well, what we have to consider is the phase of the sine function. We're calculating this signal x of n. X of n is equal to sine of 2 pi n times f divided by fs, where f is the frequency, 440 Hz, fs is the sample rate, and n is the number of the sample. So the phase of the sine function depends on the value of n, and that's what we saw in this line of code here. Now, the default block size of Bela is 16 samples. So my question for you is, what range of n would you encounter in that for loop inside that block? When we were running the original Sine Generator code, n would become quite large. It would start at 0 and it would go all the way up to the end of the buffer, potentially tens or hundreds of thousands of samples. Instead, on Bela, n is going to take only a range of 0 to 15 because that's as many samples as we're calculating within one block. So the render function is going to calculate 16 samples at a time. N will start at 0, it will go to 15, and then the next block is going to start over and n is going to be equal to 0 all over again. Something to try is just to go change the block size in the settings tab of the Bela IDE, and you will find that that should produce a different but equally horrible buzzing sound. Why is that? Well, in that case, it's because n is going to take a different range of values, starting at 0 and maybe going to 31 or 63, but certainly not incrementing smoothly from the beginning to the end of the sound. Basically, what's happening is this. What we're getting is the picture on the top, where every real-time block that we calculate starts all over again from the beginning. We calculate the first 16 samples of a sine wave, and then when the code runs again for the next call to render, we completely forget whatever it was doing, and we go back to the beginning and start all over again. So rather than getting the sine wave that we want, we're getting this sawtooth, which is perpetually jumping back to the beginning of the signal, rather than picking up smoothly from where it left off. But what we actually want is for our code to remember where we were in the sine wave so that the next time we have a block generated, we can pick up from where we were and carry on and have a smooth calculation. How do we do this? Well, the key is that we need to preserve state. By state, I just mean remembering what we were doing, having some kind of information that persists beyond one call to the render function in Bela. So the idea is that every time the render function runs, we're going to remember where it left off and we're going to pick up from there. The problem that we have is that any variables that we declare within the render function are going to disappear by the end of the render function. When we run it again, they will have forgotten all their information. And the simplest and easiest solution is to use global variables. Global variables are variables that we declare at the top of the file rather than within any particular function. Now, if you're an experienced coder, you might say, global variables, there are so many better ways of doing that. You would be right. Of course, there are other approaches to remembering state that don't require global variables, but they tend to be structurally more complicated to implement. So for the purposes of the lectures in this course, we will often fall back on using globals. Okay, what I want you to do now, before we go on, is to see if you can adapt sine generator RT so that instead of producing that terrible buzz, it produces a smooth sine wave. And the key here is to create a global variable that's going to be at the top of the file. And at the top of the file, you're going to remember how many samples have gone by since the program started running. And so you'll declare the variable at the top of the file, and then you'll use it inside the render function to calculate the phase of the sine wave. So just to look at that briefly, the global variables are the ones that are declared here at the top of the file. Notice they're not inside of any function. So what you need to do is declare an additional global variable here at the top, and then use that as part of this calculation. Now you're going to need to do something to have that variable remember how many samples have gone by since the beginning of the program. I will leave that as an exercise to you now. Pause the video here, come back, we'll look at the answer. Okay, so hopefully you got that working. Here is the general form of what the answer might look like. And I've condensed the salient code here just to make it easier to follow. First of all, let's talk about what's happening in the render function. Render is being called once per block by the Bela system. What that means is that every 16 samples, Bela is going to call your render function. Your job is to render 16 samples of audio and get out of the way. And within the render function, we have a for loop. We saw the for loop before in calculate sine, but in this case, it's going to run only 16 times. We're going to start from a value of n is equal to 0. That's the first bit of the for loop. The second bit, after the first semicolon, says n is less than context arrow audio frames. That's going to have a value of 16, and what we're saying is keep running the for loop as long as n is less than 16. The third bit says n++. The plus is shorthand for saying n equals n plus 1. So in other words, start n is equal to 0, keep going as long as n is less than 16, and increment it by 1 every time. This is going to produce a block of code that runs 16 times in a loop. Within all of this, we have a number of local variables, n, out, channel. As we discussed, these variables are going to forget their values after the end of the render function, and that's no good for us in terms of remembering where it was that we left off. So instead we have to do something like this. Here's our global variable declared at the top of the file called gTotalSamples. I've declared it as an unsigned int. That means it takes only non-negative values. You could equally declare it as an int and it would work the same way. So we're going to use gTotalSamples to remember the total number of samples that have gone by since the beginning of the program. Now, there's a couple key bits of code here that are using and updating gTotalSamples. You can see that in the sine calculation, instead of using n to compute the phase, we're using gTotalSamples, because this is going to remember its values over time. But then also notice that we have to, inside this loop, write this line, gTotalSamples++. What this means is that the total number of samples needs to be incremented once per loop. So unlike n, gTotalSamples will remember its values from one call to render to the next and will steadily increment over time, giving us a good sine wave. There are some other ways to write essentially the same block of code. Here is a way that rather than incrementing gTotalSamples every iteration of the loop, we could just increment it at the end of the block, where what we could say is we got to the end of render and we said, right, we have calculated 16 audio frames in this particular block, so what we're going to do is we're going to add 16 to gTotalSamples, and then inside the sine wave calculation, instead of just having gTotalSamples used to calculate the phase, we have gTotalSamples plus n. Personally, I slightly prefer the previous way of doing it, but either way will produce the same results. And we will explain all of this stuff involving this variable called context in the next lecture. Now I want to talk about why this works, and indeed why it's necessary. If we're implementing a real-time DSP system, then we almost always have to remember what was happening before. The only kind of DSP system that we can implement without remembering what we were doing before is what's called a memoryless system, which is to say something where the current output value depends only on the current input and no previous values of any sort. Now, that's worth unpacking a little bit. You might ask, well, is that really true? We are processing one block at a time, and does it still apply that we can't know about previous samples? For example, let's take an equation for what's called the first order difference. What this equation means is that the current output is equal to the current input minus the previous input. Y of n is equal to x of n minus x of n minus 1. And you might reasonably ask, why do we need to preserve state across calls to render when we have potentially multiple samples in a block and we can oftentimes see the current and the previous samples within the same block? So, for example, if we wanted to calculate y of 3, that's x of 3 minus x of 2, and we don't need to save any state and global variables to do this because all of that is available within one block. So what's the counterexample? Well, the counterexample is something like this. Y of 16 is equal to x of 16 minus x of 15. The problem that we have here is that x of 15 was in the previous call to render, and if we didn't bother to save it, it's gone and we're never getting it back. So what we can see here is that even the simplest of DSP systems, unless they're completely memoryless, we're always going to need some kind of state that is recalled from one call to render to the next, and that's what we use the global variables for. So that's a first step toward real-time audio code. Let's just run this to make sure that it works. So here's unsigned int, g total samples equal to 0. You can see that we're incrementing at each iteration of the for loop, and we're using that in the calculation. So if we go and we run that, then indeed, there we are. Now, there's a problem here, and it's a subtle one, but it will bite us if we don't solve it now. The problem is this. What happens if the frequency changes? We've been calculating x of n is equal to sine of 2 pi n times f over fs. If the value of f, which is the variable g frequency, changes after some period of time, we might encounter a problem. What would that be? Well, the problem is this. So here's a couple calculations for two almost identical frequencies, where we've calculated the phase based on the frequency, based on n, and based on the sample rate. So at 440 Hz after 5 seconds, the sine wave would be at a phase where it had a value of 0. Whereas if the frequency was 440.01 Hz, it would actually have quite a different value of about 0.3. So the problem that we might have is that when the frequency changes, we might have a sudden jump in phase. And what that can produce is potentially a click or a pop, or possibly even worse. Now, try it for yourself. Go back to the code that you just wrote and add this particular line to the end of it. G frequency times equals 1.00001. And this goes right at the end of render, after the end of all the for loops, but right before the very last curly brace. So pause the video here, try this now, and see what it sounds like. So let's try that. What we're going to do is we're going to say G frequency times equal 1.00001. Now, what is this expression, by the way? Star equal. What this means is it's another shorthand. G frequency is equal to G frequency times 1.00001. And it's just a way of saving space when we are writing our code. So if we run this project now, you will hear that the frequency will gradually increase, but it won't necessarily still sound like a sine wave. Quite enough of that. So you can hear that we get this strange distortion that increases as time goes on. The reason that this is happening has to do with the phase of the sine function. Sine takes a range of values between 0 and 2 pi. The geometric intuition here is that the sine function is giving you the y or vertical coordinate on the unit circle corresponding to that particular angle. So in that analogy, what does frequency correspond to? We're generating a sine wave that has a particular frequency. What does that mean with respect to phase? So frequency is in fact the derivative of the phase. So when we talk about the frequency of our sine wave, what we're talking about is effectively how fast we're spinning around this circle over time. Why is this a problem? So in our old code, when we change the frequency, we are perpetually recalculating the phase based on the number of samples that have gone by. But if we change the frequency, that phase might suddenly jump, which would produce a click or a discontinuity, and when that's happening regularly, every single call to render, that's where that distortion starts to sneak in. So we're not actually getting a smooth sine wave. If you were to put it on an oscilloscope, you would see that there would be lots of breaks and jumps in it. So the big question is, what should we do instead? And my suggestion is that rather than remembering the number of samples that have gone by, it's much more convenient simply to remember the phase, remember where we left off in the sine wave and continue from there. So how do we do that? Well, in the previous code, we were always recalculating this expression, 2 pi n times f divided by fs. That gave us the phase as a function of the frequency, the sample rate, and the number of samples that had elapsed. Instead, what we should be thinking about is storing some kind of variable that stores the phase itself. I'm calling it phi here in my equations. You might want to give it a name like g phase in your code. And then what you're going to do is every time you're just going to take the sine of phi, or g phase if that's what you call it, and having done that you will then update the phase according to the third of those equations here. Phi is equal to phi plus 2 pi times f divided by fs. So we're actually implementing exactly the same thing, but notice there's no longer any explicit dependence on this variable n. Instead, implicitly, we are incrementing the phase by the right amount between one sample and the next, and storing the phase in a way that we remember it between calls to render. So pause the video again here, see if you can implement your oscillator code that way, and see whether that smooths out for you the weird timbre of that sound. Your code will probably look something like this. Again, I've just pulled out the most salient bits. The things I want to highlight here, first of all, is the global variable called g phase, which is remembering where on the unit circle we were. What is the phase of the sine wave at any given time? The next thing is that every iteration through the for loop, we are incrementing the phase by a certain amount, which is equal to 2 times pi times f divided by fs. Notice there the plus equal operator. That means g phase is equal to g phase plus something. And notice that there's no longer any reference to n specifically. And then the actual calculation of the sine wave becomes a whole lot simpler. We just take sine of g phase and that's it. And what's happening is that every iteration of the loop, the phase moves on a little bit, and that is what's giving us our sine wave that's changing over time. So why don't we run this code and see what happens? Here I've got my implementation of that code with g phase as a global variable, incrementing it at the top of the render function, and then using g phase inside the calculation. Now I can run this code, and we should hear that the strange timbre goes away. But as we go on, you're going to hear that there's a slightly different, slightly strange problem. Where's that stair-stepping coming from? The frequency doesn't seem to be incrementing smoothly. Instead, it seems to be jumping every few seconds. Why is that happening? This is a very strange problem indeed. Well, there's a slightly subtle issue, which is that g phase is getting bigger and bigger and bigger. G phase is stored in a float, which is a type of variable that holds a floating point number, i.e. one that can have decimal points. The problem that we have is that there are a limited number of bits to store g phase. It's not infinitely precise, and so as g phase gets bigger and bigger, it actually starts to lose precision and lose the ability to distinguish between tiny changes in phase. So what's happening is that when we increment it every time, the bigger this value is already, the less precise this calculation becomes, which is kind of strange because it makes the frequency be rounded to some slightly strange value rather than being exactly what we expect. So the problem here is loss of precision. And there's actually a relatively simple solution for this, which is to wrap the phase around when it exceeds 2 pi. Because there's no reason that g phase needs to get arbitrarily large. The sine of 4 pi is equal to the sine of 2 pi is equal to the sine of 0. So if we just add an if statement like this, which says if the phase is greater than 2 pi, subtract 2 pi from the phase, then it will always stay in range, and then we will have the effect that we want. And let's try that now. Much better. So there we have it. We have taken code that was originally not in real time and we have adapted it to run in real time. And the crucial ingredient for making this happen was to remember where we left off, because the render function is only calculating one tiny slice of time for our real-time signal. And every time the render function runs, it is up to us to remember where it is that we left off and pick up from there the next time round. And what we're going to see in the ensuing lectures is that this principle of remembering the state applies very widely across real-time DSP systems. I'll leave you with one last bonus task for this lecture, which we won't go through together, but maybe we'll look it over the next time, and that is to make your code generate 2 sine waves rather than 1, to have 440 Hz playing through the left channel while you have 660 Hz playing through the right channel. Just to note that you'll need to change this for loop inside of the render function, which writes the same signal to each of the channels. Just delete the for loop and call audio write twice. First write to channel 0 with one value, and then write to channel 1 with a different value. Finally, when you're done, don't just pull the power. Remember to shut down the board gracefully using either the power button in the IDE or holding down the white button on the Bela cape. This is so you don't lose any data when you shut down. You can find us on social media at Bela Platform. We have a forum where you can ask questions. We have a knowledge base at learn.bela.io that has a wide variety of documentation and help materials. We also have a blog at blog.bela.io that features projects made with Bela, and you can find more resources at the link at the bottom. Thanks very much for following along. Don't forget to click subscribe to be notified of each new lecture as they become available. See you the next time.